Okay, let's finish this week's lectures from me by looking at Al-Khwarizmi's algebra. Okay, first, let's have a look at this interesting Arabic phrase. I guess it's Algebra wa al-Muqabala. So this is the Arabic phrase which describes transforming an equation into a standard form. And the idea is once it's in a standard form, you can apply the appropriate algorithm and solve it. So the first word there, algebra, means restoring, sort of making all the terms positive. So for example, if you're given an equation like 3x plus 7 equals 8 minus x, then you want to get rid of all the minus signs, so you bring the x's over, and then you write it as 4x plus 7 equals 8. And when you're doing that, you're doing algebra. So an interesting comment is that the medieval term, Spanish term for a bone setter was an algebrista. So just emphasizing the word restoring there. So wa is just and in Arabic. And then the last phrase there, al-Muqabala, means meeting or maybe meeting place. And that's where you've got terms of the same type and you sort of amalgamate them into one term. So for example, if you've got 4x plus 7 equals 8, 7 and 8 are of the same type, so you amalgamate them, so you bring the 7 over, take it away from the 8, so you get 4x equals 1. So you're just left with just one of each type, and the coefficient has to be positive. And that's doing algebra wa al-Muqabala. So really, the foundational text of modern algebra is the condensed book on the calculation of algebra wa al-Muqabala. Written by our friend Al-Khwarizmi around 820 in Baghdad. Remember, we saw him earlier. He did the book on arithmetic. So remember, we got the name algorithm from the word algorithm from his name. So it was translated into Latin in 1125 by Robert of Chester. I think it was in Toledo or Cordoba, somewhere in Spain. And it was translated as Liber, which of course is Latin for book, Liber Algebrae et al-Muqabala. And so we see this whole thing about when you translate things as well, you can either try translating them into actual words in the language, like Liber and et. Et is book and but the algebrae and the al-Muqabala, he didn't have an appropriate Latin word for those, so he just sort of transliterated it over from Arabic into Latin. Okay, so in this book, he only dealt with linear and quadratic equations. So that means there's only 3 different types of quantities. There's simple numbers like 2, 3, 4, etc. And he called them dirhams. So remember, dirhams was the currency, the coins that were used over there. Then the unknown was known as a root or a thing in Arabic, that's shay. When it got translated into Italian, it became cosa, which is Italian for thing, and that's why, in old-fashioned way of speaking, algebra is known as the Cossack art, and numbers like unknowns like x and y and z are known as Cossack numbers, coming from thing. And then the square of the root is mal, which means wealth. And so we kind of see that wealth, that sort of goes with the numbers being dirhams. So that means there are 6 different types of equations, whereas we would think there were only 2 different types of equations, right? We would just think there were linear equations and quadratic equations. So roots equals number, that's a linear equation, okay? But they also had mal equal roots, x squared equals nx. And notice here 0 would not be considered a solution. The solution, of course, is just n. Whereas for number 1, of course, the solution is just m divided by n. So m and n are positive numbers. They don't have to be integers. Okay, equation 3 is mal equals number, x squared equals m. And of course, the solution for that is just square root of m. Not plus or minus square root of m, square root of m. And then the last 3 cases are the different types of quadratic equations. M plus x squared equals nx, m equals x squared plus nx, and x squared equals m plus nx. So you might think, oh, what about x squared plus nx plus m equals 0? We'll see that's not allowed because we need solutions which are positive numbers. Okay, so let's have a look at an example of a problem he gave. So this is one where we've got mal and 21 equals 10 roots, or how we would say it, x squared plus 21 equals 10x. And he does things as usual, completely rhetorical. He says, half the number of roots, it is 5. Multiply this by itself and the product is 25. Subtract from this the 21 added to the mal and the remainder is 4. Extract its square root, 2, and subtract this from half the number of roots, 5. There remains 3. That is the root you wanted. Alternately, you may add the square root to half the number of roots and the sum is 7. This is the root you wanted. Sorry, I missed out root there. So the first part, that is a verbal description of 10 over 2 minus square root of 10 over 2 squared minus 21. And the second part is 10 over 2 plus that square root. Okay, and you should be able to recognize this is exactly the quadratic equation. Okay, nothing too dramatic. The really interesting thing is that this is really the first time that they give the procedures for solving these equations, and then they give a sort of proof of validity of the procedure. Okay, and so what happens in this proof is that equation is interpreted as squares and rectangles, right? Remember we had x squared plus 21. Well, you look there, you've got a square x squared, and then you've got another square x by 21 divided by x. Okay, so that equals 10x. So we can write as a rectangle in 2 different ways, as 10x and as x squared plus 21. Okay, and of course the key is we take the number of roots and we halve them. So we have to take 10 and we divide it by 2, we get 5. And if you think about it, there's 2 different places where the line can fall. So the 5 can either be within the x squared or it can be outside the x squared. And so we'll look at this a bit closer, analyze it a bit closer later, and we'll see this is why we get 2 possible roots for this example right here. This is the justification of this comes from Euclid. I think it's Euclid Book 2, Proposition 5. That goes into that. Okay, and then interestingly, he writes some remarks on this case. Okay, so notice, oops, we would write this as n on 2, that should be plus or minus square root of n on 2 squared minus m. Okay, so he makes some comments of that. So this is very standard. You give the procedure, prove its validity, and then you give commentaries saying interesting things about what is happening. So in this case, both addition and subtraction can be used. So you can do that plus or minus, which will not serve in any of the three cases where the number of roots is to be halved. So that is, this case here, out of cases 4, 5, and 6, is the only possible situation where you have two positive roots. And then he makes some comments on the discriminant that underneath the square root there. So we know that that can't be negative. So, and he actually makes that comment there. Know also that when in a problem leading to this case, you have multiplied half the number of roots by itself. If the product is less than the number of dirhams added to the mole, then the case is impossible. So that is, if n over 2 squared is less than m, we would say the discriminant is negative and there are no solutions. And then it goes on to say, talking about when the discriminant is 0. On the other hand, if the product is equal to the dirhams of cells, then the root is half the number of roots. So if the thing under the square root is 0, then you've just got n on 2, and that's the only solution. And then, interestingly enough, he says that if you're given the case m plus px squared equals nx, you can just divide through everything by p, and you'll get m on p plus x squared equals n on p times x. And this shows that he's not just interested in cases where the coefficients are whole numbers. Okay, that will do us for this week, and I'll talk to you soon.